Welcome to our presentation on a compressive sensing camera. I'm Omar, and I will be presenting our camera alongside my partners Cole, Gassan, and Mazin for our client and sponsor, Stephen Knutson. Unlike a regular camera, which uses an array of sensors, a compressive sensing camera uses just one pixel to capture images by using a spatial light modulator to overlay frequency domain masks that can be used by our reconstruction algorithm to generate an image, utilizing a sampling rate of only 25%. Our project was expected to capture a simple scene in under 10 minutes, store the spatial data on a removable SD card, and use it to reconstruct a 64 by 64 black and white image via reconstruction software. We also had a stretch goal to include the training of a convolutional neural network, or CNN, to help with the reconstruction. Overall, our camera was able to capture a scene in only about 2 minutes and store that data onto an SD card. Our reconstruction software was able to reconstruct general shapes from the scene, and we were able to train and implement a CNN to improve the reconstruction.
This is our camera. It is USB powered and can be plugged into the wall or into a computer. To capture an image, load an SD card into the camera. The LED will switch from red to green. To take an image, press the button. When the green LED stops blinking, the camera has completed capturing an image. At this point, you can remove the SD card. Insert the SD card into your computer. In the reconstruction software, you can open your capture file. And then you can choose to select which reconstruction algorithm you'd like to use. Finally, you can save the image back to your computer.
Moving on to the hardware design, let's start with the lens assembly fixed to the front of the camera. The assembly is comprised of a convex objective lens and a concave eyepiece lens to project an upright but shrunken image onto the LCD. The LCD here acts as our spatial light modulator by displaying grid-like patterns to selectively block and emit light from different parts of the scene. This light is then collected and focused onto our single photodiode placed at the center of our circuit board. The board itself also features a Raspberry Pi Pico 2 acting as our main controller and an SD card holder for data transfer. On the back side, we have a red status LED that reminds us to insert our SD card before capture, a green status LED that indicates both ready and in progress states, and a physical button to initiate capture.
The image capturing subsystem, we selected the Raspberry Pi Pico as the main controller. Some of the main reasons is that it provides reliable real-time performance, which is important for time-sensitive tasks like pattern projection and sensor sampling. It has enough GPIOs and communication interfaces to connect to all the peripherals. In terms of peripherals, we use a push button as a simple user trigger to start the data acquisition process. The LCD display is used to project the Welsh mask pattern onto the scene. A photodiode captures the reflected light intensity of each pattern. The SD card is used to store all measurement. Store all measurement data for offline reconstruction. And finally, we use a serial communication interface mainly for debugging and monitoring during development. Now let's walk through how the firmware operates during a measurement cycle. First, the system initializes all required subsystem. This includes, as we've mentioned before, the push button, the LCD, the photodiode, sensor, the SD card. This ensures that the entire capture pipeline is ready before any acquisition begins. Next, the firmware waits for the user start signal. the system remains idle until the user presses the button, which starts the capture process. After the system is triggered, it enters the acquisition phase with periodic calibration. Instead of calibrating just once, the firmware performs calibration every 10 masks. During calibration, it displays fully black frame and a fully white frame to capture reference readings. This is important because light source might fluctuate over time, which would introduce measurements errors unrelated to the image itself. In addition, the photodiode dark current can drift due to thermal effects. By recalibrating every 10 masks, we compensate for both ambient light variation and sensor drift, improving measurement accuracy. Between calibration steps, the system performs the main acquisition. For each mask, the firmware selects a random Walsh mask index, generates a 64 by 64 pattern, and displays it on the LCD. After a short stabilization delay, the photodiode is sampled 5 times, and the readings are averaged to reduce noise. This average value is then stored. Once all measurements are complete, the firmware writes the collected data to a file on the SD card. This includes both the measurement values and the periodic calibration references. Finally, the system safely deinitializes the SD card interface to ensure all data is properly saved. Overall, the firmware implements a robust acquisition pipeline with periodic recalibration and randomized measurements to ensure accurate and reliable data collection for offline image reconstruction.
The software interface for the reconstruction algorithms was centered around user accessibility. That's why we decided to build this within the MATLAB App Designer, which allows us to create a GUI that is easy to use. The App Designer GUI allows users to easily open files that they would like to use, select the reconstruction algorithm they'd like to use, and view the image before they save it. There is also a desire from users to be able to process multiple images at a time. The SD card can hold many capture instances, so the software is built so that many files can be processed at once. There is a bulk mode, and the user can select multiple files and process it with the push of a single button. There is a progress bar for them to be able to check how long it's going to take. There are 3 reconstruction algorithms available to the user: a simple back projection algorithm, a total variance minimization algorithm with edge preservation, and a custom convolutional neural network which takes the linear back projection and removes the artifacts from it. Since the reconstruction app is open source and designed to be modular, it is very easy to add your own version of a reconstruction algorithm to test on image data.
Now that we have an understanding of the camera components, let's talk about which parts did and did not work. Our software was able to successfully reconstruct spatial data out of the frequency domain, and the CNN we trained was able to improve upon its output. The firmware successfully established a control loop that managed both user interfacing and data collection. Our biggest limitation, though, was in the hardware, specifically the light path. Not only are optics very particular and sensitive, but the fundamentals of the LCD impaired our ability to collect the required light. The LCD features a polarizer that is essential to its function, but that also cuts light intensity in half. Additionally, the crystals in the liquid crystal layer are large enough to scatter light in all directions, obscuring the scene in the areas of the mask that are meant to be transparent. These 2 features introduce significant noise into our capture data and reduce the resolution of its output.
For future work, there are several clear directions that could significantly improve this project and move it beyond the proof of concept prototype. The first major improvement would be to redesign the hardware into a custom printed circuit board, or PCB. Right now, the prototype relies on separate breakout boards and prototyping hardware, which makes the system bulkier, less robust, and harder to package neatly. Moving to a PCB would reduce the overall size of the camera, simplifies the wiring, and improve reliability. The second area for future work is improving the user experience by making the system more integrated. In the current prototype, image acquisition happens on the camera hardware, while image reconstruction is done later on a separate computer using MATLAB software. That worked well for development and debugging, but it's not the most practical setup long time. A future version could move toward onboard or embedded reconstruction, where the camera itself will perform at least part of the reconstruction process, reducing manual file transfers and making the capture to result process more seamless for the user. The third and most important improvement is upgrading the sensing and modulation hardware. Transparent LCD helped keep the prototype low cost, but it introduced a major limitation. It did not block light perfectly, so the difference between the black and transparent states was too small. This reduced the measurement range and image contrast, and additional light attenuation and scattering further lowered image quality. A higher quality modulator or possibly a DMD would improve contrast, optical efficiency, and overall performance. Finally, future work could also target stronger performance requirements. The current goals, such as 64 by 64 image resolution and proof of concept acquisition timing, were mainly chosen to demonstrate feasibility. A next iteration could aim for higher resolution, faster acquisition, improved measurement stability, and even new requirements such as operation at wavelengths like infrared. Altogether, these improvements would move the project from an academic prototype toward a more practical, research-oriented imaging system.
In conclusion, our team was able to successfully create a compressive sensing camera that eliminates the need for a sensor array by spatially modulating light into the frequency domain and collecting it all onto one pixel. This data was used to successfully reconstruct the spatial image via our reconstruction software and was even improved upon by our personally trained convolutional neural network. The project serves as a proof of concept and leaves a clear path forward to improve the resolution and quality of captured images. Thank you for watching our presentation, and feel free to reach out for any questions.